When people think about robots, they usually imagine something like a Boston Dynamics robot, metallic and humanoid. But the robots we'll see in the future might not look like that at all. I mean, if humans are interacting with something on a daily basis, it's probably best not to make it sharp, delicate, and heavy.
How rude!
Instead, advanced robots might be made safer if they're soft, flexible, and all kinds of shapes and sizes. So instead of Sunny from iRobot,
No.
something like Baymax from Big Hero 6 might be closer to what's in our future. This is a compilation video of 5 of my videos on the surprisingly different ways robots can look and why we build them that way. This is my first time trying out a series, and honestly, it's been a busy time for the Veritasium team. We're working on some exciting things in the background, but in the meantime, we wanted to put this together for all of you. And I also caught up with Dr. Elliot Hawkes, the scientist behind 2 of these robots, to get an update on how they're progressing and when we can expect to see them in our lives. Are there more developments happening with the jumping robots?
We have a whole nother project on jumping, and it doesn't even use springs, so I won't give away our secrets yet, but keep an eye out for that one too, because that's gonna be fun.
So you have another jumping robot which has a totally novel design.
Yep.
And you think it's gonna be better than the one that you had before?
Correct.
And I just want to shout out our longtime sponsor, Brilliant. They've supported the channel since 2021, and it's great to get to talk about something that I actually use myself. I've had Brilliant on my phone for years, and it just allows me to learn something new every day instead of, say, doom scrolling. You should make valuable use of your time. So I will tell you more about Brilliant later in the video. Non-humanoid robots aren't just safer for us to interact with. One of their biggest advantages over traditional robots is that they don't just do things humans already do but better. Instead, they're specialized to master entirely new abilities, often ones that no human can tackle. This is a robot that can grow to hundreds of times its size, and it can't be stopped by adhesives or spikes. Although it looks kind of simple and cheap, it has dozens of potential applications, including one day maybe saving your life. These robots can be made out of almost any material, but they all follow the same basic principle. Powered by compressed air, they grow from the tip.
That's good.
And this allows the robot to pass through tight spaces and also over sticky surfaces.
Something like a car will get stuck to it. It gets stuck in the wheels. Now if I do the same thing with the Vine robot, see the robot is able to extend.
It can navigate this curvy and twisted passageway effortlessly, which suggests some of the applications it's well suited for. Now you might think spikes would be the downfall of an inflatable robot, but even if it's punctured, as long as you have sufficient air pressure, the robot keeps going.
And you might be able to hear it. It's actually leaking now, so I'll have to turn up the pressure. This by itself is not yet a robot, but once we had steering, a camera, some sensors, and maybe some intelligence as to where we're directing it, then we could say it's a robot. So this is sort of the backbone of our robot. This is what allows us to build our type of robots.
So where did the idea for this device come from?
I had a vine in my office that was on a shelf, and it was kind of out of the sunlight. And over the course of like a year or so, it slowly grew out this tendril out and around the edge of the shelf and towards the sunlight. I said, that's a pretty cool thing it just did, right? Yeah. So you started thinking, well, is there a way you could do that robotically?
The solution is really elegant in its simplicity. Just take some airtight tubing and fold it in on itself. It's kind of like a water wiggly, those toys that are really hard to hold. When you inflate it with compressed air, it starts growing out from the tip. And if you want the tube to always bend at a certain spot, you could just tape the tubing on the outside to shorten one of the sides. For example, you could tape it into a helical shape to create a deployable antenna. What about getting them to retract?
Yeah, that's a challenging problem. When you're in a constrained environment, all you really have to do is pull on, we call it the tail, so the material that is passing through the core of the body. You pull on it and it basically ungrows. It just goes back inside itself. Now, if you're in a big open area like this and you try pulling on that, instead of inverting, so retracting, it tends to kind of coil up and make a ugly shape.
And the engineers have come up with ways to retract the tube to prevent it from buckling using internal rollers. But the tube doesn't have to be the same diameter the whole way along. Here there's actually a much wider section. Think of it like a pillow that's packed into the end of the robot.
Yeah, if you could sit cross-legged on it.
Cross-legged on the table. This sounds super sketchy.
So it grows underneath the table, just as usual, and then as the pillow part starts inflating,
What? Is this not good, or is this okay?
it can actually lift me up.
So my balance is not great, as we can see. Stand on it?
What's amazing is that this doesn't require much pressure above atmospheric. Just a tenth of an atmosphere applied over a large area like a square meter can lift something as heavy as 1,000 kilograms, all the while remaining soft.
Whoa. Woo. That was great.
That's the paradoxical thing about pressure. You can get a large overall force with low pressure as long as the area is large enough.
Right.
What sort of area is that pillow there?
It's 600 square inches, right? So with 1 psi, 600 pounds.
Yeah.
Yeah. 2
It's just
psi,
crazy.
1,200 pounds.
And the whole time it feels really soft.
Yeah, because there's a couple psi, right?
It's important that the device is still soft so it doesn't hurt anyone.
So you can design these things to have cross-section that changes along its length. So it could be a very small body that could grow into, for example, a collapsed building and potentially lift a large object off someone who's trapped or maybe in a car crash or something like that. It can apply huge forces with very soft and lightweight, cheap materials.
These robots can also be deployed in search and rescue operations by attaching sensors like a camera onto the front.
These robots are actually really hard to stop, so you can take them, grow them into a clutter, potentially a collapsed building or something like that, and they will continue to go somewhere. An alternative is they're so cheap, I mean, they're basically free. You could grow 100 of them, let's say, into a collapsed building with some sensing on them, and maybe only one of them finds somebody, but that's a huge success if it does.
But how do you keep a camera connected to the front of the robot when it grows out from the tip? Well, one way is to use an end cap, which allows that camera just to stay on the front, pushed from behind by the robot. But there are other mechanisms of attachment. The tiny wireless camera is mounted on an external frame, but this frame interlocks with an internal frame, which is actually inside the pressurized part of the robot body. It's similar to how a roller coaster's wheels go around the track, so this prevents the camera from falling off as the robot grows. What's really interesting is how the Vine robot can be actively steered. They attach artificial muscles to the robot. So the way this muscle works is that if you inflate it, it expands sideways, which leads to it contracting in length.
We don't actually use these much anymore because although it's soft, it's still somewhat stiff. So what we use instead are simply tubes of this ripstop nylon fabric with the braid oriented at 45 degrees. So in this sense, we just have one single layer of airtight fabric. This is the main robot body here. Then we have 3 pneumatic muscles connected to it. Now these 3 muscles are each connected to their own air supply, connected to regulators over here. As the robot extends from the tip, we can steer it by shortening and lengthening the sides. So just the way your hand works is if I shorten this tendon in my arm, my hand will move this way. Or if I shorten the one on this side, it'll move the other way. So our Vine robot, we have these muscles along its side, so as they inflate, they'll turn it one way, then if I inflate the one on the other side, it'll turn the other way.
So the Vine robot can fit through tight spaces, it doesn't typically get stuck on anything, and isn't bothered by sharp objects. And once you attach that camera on the front, it's ideal for things like archaeology. The robot was actually taken to Peru to investigate some very narrow shafts.
So we were looking at this archaeological site that was built somewhere between 1500 and 500 BC in the Andes Mountains of Peru. And it was an ancient temple that had all these underground spaces. And part of what the archaeologists were doing was trying to understand what the spaces were for and what the people who built them were trying to do with them. So part of that was unknown, but there were these giant rooms that they called galleries, and then there were these small ducts or tunnels that were offshoots of these rooms, and they wanted to know where these ducts led, but they were too small for a person to go in. So we were able to successfully use the Vine robot to explore 3 of the tunnels that couldn't have been seen through other means, which was super exciting, and we got video inside the entire tunnels and gave it to the archaeology team.
There's an application where I feel like this solution is just so obvious, I wonder why it didn't exist before.
Intubation is literally the process of putting a tube into a patient. The purpose is to breathe for the patient when the patient isn't breathing. And so traditionally, a highly trained medical professional would take their laryngoscope, come above the patient, and once they see the trachea, you start to pass your tube down inside. I'm almost there. I can see the light. So if you can see right now, I just got it in to the trachea.
Oh yeah.
Right there. And it took me a couple minutes, and I was really kind of wrenching on this patient here. If there's somebody who's not breathing, every second counts.
But by using a miniature version of this Vine robot, researchers are hoping to make intubation faster and safer.
Somebody like me with no training could pretty simply insert this device, aim towards the nose, and just like that, if you can see, we've already intubated. And all it took was a little bit of pressurization. Just like that.
It almost looks like a sort of a party favor.
Yeah, right? It's like, this reminds me a lot of those inflatable, kind of like Play-Doh structures you see at car lots.
How does it know to go down the right tube?
Yeah, so that's one of the kind of cool things about soft robotics is the robot is quite compliant. And we see that in a lot of these demos, they can squish, they can bend. And so how we've designed it is that the main robot goes down into the esophagus, and then we have this side branch that heads towards the trachea, and it's quite flexible, and so it basically finds the opening. So it's a really neat example of kind of a passive intelligence, mechanical intelligence, some people call it, where it can find its path even if we don't know exactly the shape beforehand.
Have you tried this on a real person yet?
Not on a real person, but we've actually tried this in a cadaver lab, and we've shown that we can move from this nice idealized version to an actual in vivo situation and successfully intubate a patient.
There's another application, which is burrowing into sand or soil. When you blow compressed air into something like sand, it fluidizes. It becomes like a liquid, and that can allow the Vine robot to grow into granular materials like sand.
If you've ever been to the beach and you try to stick like your umbrella pole into the ground, it's fairly difficult.
And then try to push that probe down into the sand, no fluidization. Yeah, it feels like it sort of gets wedged in there.
So now I'll turn on the air.
Oh yeah. You can feel it immediately. Oh wow. Yeah, that's a lot.
So what we've done here is essentially we just blow a jet of air out the front of the robot, and that loosens up the sand enough to reduce the force of the sand so that the robot, just by tip extension, can make its way through.
This makes Vine robots an attractive option for NASA when they look for ways to study the surfaces of other planets.
Recently on Mars, they tried to have a burrowing robot, but it got stuck. Could you do it better, basically, with this?
Yeah, that's a good question. So the Mars InSight mission, they have this heat probe. The idea there was to be able to sort of hammer its way down into the core and then place a sensor that could detect the temperature of Mars. However, the problem they ran into there is that it turned out the material that they put it in was more cohesive than they expected. Inside the robot, something would wind up, then pound it down, wind up, then pound it down. But it turned out there wasn't enough friction between the probe and the sand. So what was really happening was it would wind up, pound down, wind up, pound down, wind up, pound down. So it would never actually go anywhere. The advantage of something like this, like tip extension, is you'd have your base, you start at the surface, and you just keep extending your way down. You're not necessarily relying on the interaction with what is surrounding it to make it work.
What amazes me about Vine robots is how a plant inspired this simple, elegant design. It's so easy, in fact, that you could build one yourself in as little as a minute. There are instructions online that I'll link to. But from that basic design have come a huge variety of robots, with different applications from archaeology to search and rescue, or intubation to space exploration. And what else can you think of to do with it?
I've actually gotten a lot of emails from viewers about crazy ideas that we hadn't thought of, so keep them coming. We love to hear your ideas.
Are there any ideas that you can share with us that are like, oh, like that's actually really cool? That's
One idea was for clearing mines, landmines. So the idea was that you'd actually run a vine robot through the field and then detonate the landmines and basically make a path that civilians could walk through the field. So I thought that was a kind of a cool idea.
Do you think they'd create enough pressure to, trigger these things?
I think the idea was they were going to actually put explosive in the vine to detonate the the landmines themselves. Yeah.
I mean, I'm also thinking, now that you mention that, like, I'm thinking you could put, like, metal detector type sensors on the vine robot.
Absolutely.
So,
Absolutely.
spread them across the field and they'll pick up where the mines are.
I'll give you another crazy example. Another one was for space applications of putting docking. So two spacecraft docking together, you have to make an airtight seal. And so the idea was, well, maybe you could use a vine robot to do this.
Some sort of like airlock or something going out in there.
Yeah, so basically, you can imagine the two kind of tubes coming together, not sealed, and then the vine robot growing through and basically making the seal.
Are there any updates about the vine robot? Like, have the medical trials gotten anywhere?
So we just did a trial with emergency medical practitioners using our device. We gave them 5 minutes of training. We gave them the device, and they were 90-ish% successful in intubating in very rapid, something like 20 seconds.
Oh wow!
The nice thing about our device is that if it fails in 20 seconds, and so it doesn't take 3 minutes to attempt and then realize you didn't get it. I think there's something really nice about that, is that it is so rapid and easy that even if it does fail, you get another shot.
Yeah, I mean, that one seems like it's so close to actually having a big real-world application. I mean, how common are intubations?
So intubations in the OR, so operating room, are quite common. I think like 15 million a year. That's probably not our initial target because those are very reliable, like 99% plus. The kind of the fundamental problem is that the tools are designed for those doctors in those scenarios. And what happens is those similar tools get put out into the field an ambulance. And a paramedic is trying to do an intubation, but they're doing it maybe in the dark with someone in a poor body position where there's blood in the mouth. So our device takes that required skill out and basically lets the vine robot find the way into the trachea. And so pre-hospital, there's around 1 million intubations a year, and we think there's many intubations that aren't even attempted because the tools just aren't there. And then our kind of long shot is eventually, how there's AEDs, the defibrillators everywhere. One issue there is there's not a way to help the person breathe. Possibly, if we can make this thing so simple, it could basically be packaged with an AED where you could both get the heart going and you could intubate and get the oxygen in. But I think we're close. It's pretty easy. You'll have to come back and get another video. We'll let you intubate a cadaver. That'll be fun.
So we've kind of answered this question, but are these vine robots, still being worked on?
We have a project right now on anchoring, especially we're interested in. So if you think of a plant root, if you ever try to pull out like a small like shrub or something, it's incredibly hard, right? Like you're looking at this, it's got like a half an inch stem, and you're pulling on it. It's like hundreds of pounds of force. So like, how is this possible? And I think one of the coolest things is that 100 pounds of anchoring force was created with almost no reaction force initially. And there was like a seed that slowly grew down into the ground, right?
It's like all these little tendrils, and I'm imagining sort of the friction sums over all of those.
So basically, when you're trying to go into the soil, the thing resisting you is the surface area of the tip. That's what you're pushing in. And then what's giving you the anchoring force is the surface area on the sides. And so you can imagine if you clump them all together, the area in the tips doesn't change, but the surface area of the sides went down. So you basically want to split them up into as many, practically. So anyway, we're using that concept now to make these anchors
and we're working with NASA on that one as well. And so, it's like this deployable anchor where it's very light. You could throw it somewhere or just drop it, and then the roots grow down. Like there's 4 roots that grow down into the ground, and it was something like 100 newtons of force to pull it out.
Yeah, it sounds like a very sci-fi type thing where you could like throw the root pack down and it just like, poof, and then the roots grow out, and then you're like, oh yeah, the anchor is locked in.
Yep.
Yeah.
Absolutely.
Yeah, that's amazing. After seeing the unstoppable robot, we returned to Elliot's lab a few years later to see a robot that has conquered a totally different specialty, the art of jumping.
This tiny robot weighs less than a tennis ball and can jump higher than anything in the world. In the competitive world of jumping robots, the previous record was 3.7 meters, enough to leap a single-story building. This jumper can reach 31 meters, higher than a 10-story building. It could jump all the way from the Statue of Liberty's feet up to eye level. For something to count as a jump, it must satisfy 2 criteria. First, motion must be created by pushing off the ground, so a quadcopter doesn't count, because it pushes off the air. And second, no mass can be lost, so rockets constantly ejecting burnt fuel are not jumping, and neither is an arrow launched from a bow. The bow would have to come with the arrow for it to count as a jump. Many animals jump, from sand fleas to grasshoppers to kangaroos, and they launch their bodies into the air with a single stroke of their muscles. The amount of energy delivered in that single stroke determines the jump height, so if you want to jump higher, you have to maximize the strength of the muscle. The best jumper in the animal kingdom is the galago, or bush baby. And that's because 30% of their entire muscle mass is dedicated to jumping. This allows the squirrel-sized primate to jump over 2 meters from a standstill.
It has very small arms and upper body, and it's just like huge jumping legs. It doesn't have better muscles or anything, it just has more of them.
There are some clever jumping toys.
I feel like they're very...
I used to play with these poppers as a kid, and when you deform a popper, you store energy in its deformed shape. Effectively, it becomes a spring. And then, just like an animal, in one stroke it applies a large force to the ground, launching itself into the air. All elastic jumpers follow the same principle of storing energy in a spring and releasing that energy in a single stroke to jump. But none of the jumping toys we had could compare to this tiny robot.
Of all the things that I have ever tried to film, this is the most challenging.
Because it's so small, it accelerates rapidly and travels a huge distance on each jump. Each takeoff happened faster than we could even register. Now, jumping might sound like a niche skill, but engineered jumpers would be perfect for exploring other worlds, particularly where the atmosphere is thin or non-existent. On the moon, with 1/6 the gravity of Earth, this robot would be able to leap 125 meters high and half a kilometer forward. Rovers may struggle with steep cliffs and deep craters, but jumpers could hop in and out, fetching samples to bring back to the rover. And you don't lose much energy when jumping, so if you could store the kinetic energy back in the spring on landing, the efficiency could be near perfect. The team has already started to build an entire fleet of jumping robots. Some of them can right themselves after landing, so they can take off again right away. Others are steerable. They have 3 adjustable legs that allow the jumper to launch in any direction.
Essentially what we've done is we've added 3 additional legs that don't store energy, but rather allow it to form a tripod sort of, that allows it to point a direction and launch in that direction.
But how does this jumping mechanism work? Well, the main structure consists of 4 pieces of carbon fiber bound together by elastic bands. Together, they create a spring that stores all the energy needed for the jump. At the top of the robot is a small motor. A string wrapped around the axle is connected to the bottom of the robot. So when the motor is turned on, it winds up the string, compressing the robot. And this stores energy in the carbon fiber and rubber bands. After about a minute and a half, the structure reaches maximum compression.
How do you know when to put it down?
Basically, once the bottom there sticks inward and it can stand up, right now it would roll over.
Right.
Then you put it down.
Got it.
So, as soon as you can.
And at this point, a trigger releases the latch that's holding the string on the axle. So all the string unspools all at once, and the energy stored in the spring is released. The jumper goes from a standstill to over 100 kilometers an hour in only 9 milliseconds. That gives an acceleration of over 300 Gs. That would be enough to kill basically any living creature.
Watch out, watch out, watch out.
But how does it jump so much higher than everything else, nearly 10 times higher than the previous record holder? Well, this jumper has 3 special design features. First, the jumper is incredibly light at just 30 grams. It achieves this weight by employing a tiny motor and battery. Plus, its entire structure, made of lightweight carbon fiber and rubber, doubles as the spring. Per unit mass, natural latex rubber can store more energy than nearly any other elastic material, 7,000 joules per kilogram. And the design of the spring makes it ideal for its purpose. Initially, they tried using only rubber bands connected to hinged aluminum rods. But with this design, when compressing it, the force rises to a peak and then decreases.
Just feels like it all of a sudden got a lot easier to pull.
Another design with only carbon fiber slats requires a lot of force to get started, and then it increases linearly after that.
There is more and more force required to do this.
The ultimate design is a hybrid of these two approaches, the benefit being its force profile is almost flat over the entire range of compression.
Feels like that needs a lot of force, and now it feels pretty steady with the amount of force that I need to apply.
Therefore, it provides double the energy storage of a typical spring, where force is proportional to displacement. The researchers argue this is the most efficient spring ever made.
Sometimes the string will snap. It's not always consistent that it releases when it's supposed to.
Oh!
The string cut it. Let me go restring it. I'll be right back.
You'd probably expect that lighter would always be better with a jumper, especially if the added weight is simply dead weight rather than anything useful like a spring or a motor.
So we're adding basically a chunk of steel to our jumper, and it's going to jump higher. And the key is that we're adding it to the top. You want your body, the part that's moving, to weigh at least as much as the foot. When your body's lighter, it's basically this collision, this energy transfer is very inefficient, and you don't jump very high.
But the real secret to how this jumper can achieve such heights is through something the researchers call work multiplication. Unlike an animal, which can only jump using a single stroke of its muscle, an engineered jumper can store up the energy from many strokes, or in this case, many revolutions of its motor. And that's how the motor can be so small. It doesn't have to deliver the energy all at once. It builds it up gradually over a few minutes.
So the trade-off is kind of like time for energy.
Exactly.
And this is possible because there is a latch under tension preventing the spring from unspooling until the robot is fully compressed. Interestingly, biological organisms do use latches. For example, the sand flea, which can jump incredibly high for its body size.
It has a muscle that is attached, let's say right here, is right inside of the pivot point. So as it contracts that muscle, the leg doesn't extend, right? It's actually closing it more. But then it has a second muscle that pulls it out. It's going to shift this muscle ever so slightly outside the pivot point.
That's wild. So there's these two muscles that are working.
So here's your big power muscle, here's your trigger muscle. It's a torque reversal mechanism, and then all of a sudden it shoots.
But even though the biological world has latches, no organism has developed work multiplication for a jump from standstill, at least not internally. Spider monkeys have been observed pulling back a branch hand over hand using multiple muscle strokes stored in the bend of the branch to catapult themselves forward. There's a spider that shoots out a silky string, which they pull back multiple times in order to slingshot themselves to another location.
So it's like slingshotting itself?
Yeah, so they're called the slingshot spider.
Now, I tried jumping in moon boots to see if they would help me go higher.
Okay. Woo!
And it certainly felt like they did, but Elliot pointed out that from a standing start, they don't actually help much.
Kind of build it, and then go.
Okay.
Only if you jump a few times before can you store up some of the previous jump's energy in the elastic bands, and then that energy helps launch you higher on the following jump. For years, engineered jumping was developed to mimic biological jumping, but with work multiplication, it gained an advantage. If you can generate a large burst of energy simply by running a motor for a long time, the power of the motor is no longer the limiting factor. The spring is. So you can focus on making the most powerful spring possible. This jumper has nearly maximized the achievable height with this spring. Assuming an infinitely light motor with infinite time to wind up, the highest possible jump with this compression spring is only around 19% higher than what they've achieved. If you want to incorporate air resistance and play with aerodynamics, another way to send the jumper higher is to make it 10 times isometrically larger, leading to a 15 to 20% higher jump.
So we're in kind of an intermediate scale where we still are getting hit by air drag, but it's not as bad as the flea. If we went 10 times bigger, we could actually avoid air drag completely.
This works since if the jumper is scaled up 10 times on all sides, the cross-sectional area increases by 100, which increases the drag force, but the jumper's mass increases by 1,000, so it has way more inertia, meaning the drag force affects it less. The entire concept of work multiplication could bring robots to the next level. Currently, motors in robots have to be relatively small so they remain portable. But the simple principle of building up the energy from multiple turns of a motor over time would allow robots to store and then release huge amounts of energy, and set some world records in the process.
When we visited you, we were looking at 110 feet, and it was the record holder. My question, is that still the record as far as you know?
It is. I also challenge all the viewers to beat it because it is beatable. So I hope someone in the next few years will beat it, and if not, we'll beat our own record because it's beatable. I will say that much.
Are there more developments happening with the jumping robots?
We have a whole other project on jumping, which we also think will beat it, and it doesn't even use springs. So I won't give away our secrets yet, but keep an eye out for that one too, because that's gonna be fun.
So you have another jumping robot which has a totally novel design.
Yep.
And you think it's gonna be better than the one that you had before?
Correct.
Wow, that's extreme. And in terms of making these things applicable?
Yeah, so I mean, we do have a project with NASA. I will say NASA, our stuff with NASA moves pretty slow. Just in terms of what they really care about is getting something really, really reliable. That's if they're going to send it to the moon, it can't mess up. And so that's a slow going process. But I think that's still a goal is to get it to the moon.
It would be like the next Mars helicopter or something.
I think that's a really good analogy. So the Mars helicopter has just been doing awesome, basically being this little scout that can just go out and get some nice views of where the rover might need to go, or maybe even getting some samples. You can't have a helicopter on the moon, but you can jump, and we think we can get pretty similar performance in terms of height and stuff like that with jumping on the moon compared to the helicopter. So yeah, no, that's a great analogy. Are
there any interesting emails that came about from the jumping robot video?
So a lot of people want to make one, and I will say it's really hard. And I keep writing back, it's really hard. Every piece in that robot was, they talk about safety factors in engineering, where you're supposed to have a good safety factor, and we had no safety factors in anything. And so pretty much everything was near its failure limit, and so that just made it incredibly hard. But what we're trying to do actually right now is put together like a tutorial to make like it's not going to jump 100 feet, but it'll jump maybe 20 or 30 feet. stay tuned for that, because I think that would be a fun way to get people to build one themselves and try it out. I will say though that like if you really push the limits, what we're trying to do, wear your safety glasses and your gloves and all of that, because the number of like shards of carbon fiber I've gotten in my fingers.
Oh no. Brutal. What is the biggest thing you learned building the jumping robot?
How many things can go wrong when you're trying to build something really cool. This was years and years of failing over and over and over and over again. So I think something that sticks out to me is that it takes a lot of failure to get to success like that.
Would anyone ever say to you, well, why did it take that many years? Could you not have modeled out the springs, like done some simulations of it before you actually build the thing?
Well, no, and I should mention too that it's not like we didn't do any modeling or simulation. Like that's all part of our cycle too. But the problem is, we didn't even know what shape. We went through so many different configurations of robots, right? Like some were kind of this ball shape, but we had other robots that were more stick-like, rubber band based. It's like this crazy search over a huge space and comparing all kinds of different trade-offs, and I think it's a reasonable amount of time to make a world record, but that's just me.
The jumper robot can jump so high precisely because it's built of rubber and carbon fiber with a tiny body and massive legs. Its whole body is designed for one physical purpose. The specialization of robots is also natural in academic research, since it's easier for scientists to isolate and understand one ability. These may later be included into a single, more complex robot.
People expect sort of the Boston Dynamics humanoid type robots. Why have you investigated these sort of other very strange looking type robots?
The thing that maybe unifies all of them is they're mostly about mechanical design by robots and less so about controls and vision and AI and that side. And so often we think of what we do are kind of adjacent to core robots, but our lab isn't as focused on traditional robotics just because I find more joy myself in mechanical design. So that's what I like to do.
Do you have a personal favorite robot?
I can't play favorites with my robots.
I know, it's like picking amongst your children, like it's just impossible.
I love all my robots. I will say though that the jumper, there was a certain, like, it took a lot of learning from our failures and revising it. And so that when we finally got that one working, I think that was really satisfying.
From your perspective, how did our collaboration come to be in the first place?
Oh, wow. Okay, that's a fun story. So you sent me an email, I don't know how many years ago, maybe 5 years ago, something like this, and I ignored it. And I went into lab one day. I just mentioned to my student, I was like, oh, some guy emailed about making a video, and he's like, man, who was it? Maybe I could help out or something. So I forwarded it to him. He's like, do you know who this is? And so then we responded. And we appreciated the effort you put into like the details and getting the story right. I forget how long we had this call. I had this call with Emily, it was maybe 4 hours or something. We went through the details of jumping theory, because she wanted to get everything just right for that jumping video. As an academic, we care about that stuff and we want it to be right.
But the most specialized, perfected match between a robot's build and its abilities comes from one competition that's been refining this for nearly 50 years. Micromouse is the oldest robotics competition in the world. It's like the Formula One of robotics, but you have to see their speed to believe it.
This tiny robot mouse can finish this maze in just 6 seconds. Every year around the world, people compete in the oldest robotics race. The goal is simple: get to the end of the maze as fast as possible.
The person who came second lost by 20 milliseconds.
But competition has grown fierce.
When somebody saw my design, they said, "You're crazy."
Why is there so much tension? What's riding on it? Honor?
Honor?
In 1952, mathematician Claude Shannon constructed an electronic mouse named Theseus that could solve a maze. The trick to making the mouse intelligent was hidden in a computer built into the maze itself, made of telephone relay switches. The mouse was just a magnet on wheels, essentially, following an electromagnet controlled by the position of the relay switches.
He is now exploring the maze using a rather involved strategy of trial and error. As he finds the correct path, he registers the information in his memory. Later, I can put him down in any part of the maze that he's already explored, and he'll be able to go directly to the goal without making a single false turn.
Theseus is often referred to as one of the first examples of machine learning. A director at Google recently said that it inspired the whole field of AI. 25 years later, editors at the Institute of Electrical and Electronics Engineers, or IEEE, caught wind of a contest for electronic mice, or La Mouse Electronique, as they had heard. They were ecstatic. Were these the successors to Theseus? But something had been lost in translation. These mice were just batteries in cases, not robots capable of intelligent behavior. But the misunderstanding stuck with them, and they wondered, why couldn't we hold that competition ourselves? In 1977, the announcement for IEEE's amazing Micromouse Maze contest attracted over 6,000 entrants, but the number of successful competitors dwindled rapidly. Eventually, just 15 entrants reached the finals in 1979. But by this point, the contest had garnered enough public interest to be broadcast nationwide on the evening news. And just like the rumor that inspired the competition, Micromouse began to spread across the world.
Micromouse is for the taking. Micromouse is here and now. Take a chance and start creating.
出場前のマウスたちはこれからどんな迷路が The Micromouse?
Micromouse になるのかな。はい、まず昨年のこの大会ですね、全日本マイクロマウス大会のハーフサイズ競技部門で優勝してまして、去年作ったロボットからさらにブラッシュアップして作ってきたロボットで今年も連覇狙っていこうと思っています。
Even people in the top 2 or 3, you can see them trying to set their mice up and they can barely find the buttons to press because it's absolutely nerve-wracking. It doesn't matter what it was. It could be horse racing, it could be motor racing, it could be mouse racing. If you have a shred of competitiveness in you, you want to win, right?
Just like a real mouse, a Micromouse has to be fully autonomous. No internet connection, no GPS or remote control, and no nudging it to help it get unstuck. It has to fit all its computing, motors, sensors, and power supply in a frame no longer or wider than 25 centimeters. There isn't a limit on the height of the mouse, but the rules don't allow climbing, flight, or any forms of combustion, so rocket propulsion, for example, is out of the equation. The maze itself is a square about 3 meters on each side, subdivided by walls into corridors only 18 centimeters across. And in 2009, the half-size Micromouse category was introduced, with mice smaller than 12.5 centimeters per side and paths just 9 centimeters across. The final layout of the maze is only revealed at the start of each competition, after which competitors are not allowed to change the code in their mice.
小峰さんがおっしゃっていた宇宙人枠とはこのことか。上位争いは苛烈です。
The big 3 competitions, All Japan, Taiwan, and USA's APEC, usually limit the time mice get in the maze to 7 or 10 minutes, and mice are only allowed 5 runs from the start to the goal.
So if you spend a lot of time searching, that's a penalty.
Makes sense. So the strategy for most Micromice is to spend their first run carefully learning the maze and looking for the best path to the goal, while not wasting too much time. Then they use their remaining tries to sprint down that path for the fastest runtime possible. Solving a maze may sound simple enough, though it's important to remember that with only a few infrared sensors for eyes, the view from inside the maze is a lot less clear than what we see from above. Still, you can solve a maze with your eyes closed. If you just put one hand along one wall, you will eventually reach the end of most common mazes. And that's exactly what some initial Micromouse competitors realized too. And after a simple wall-following mouse took home gold in the first finals, the goal of the maze was moved away from the edges and freestanding walls were added, which would leave a simple wall-following mouse searching forever. Your next instinct might be to run through the maze taking note of every fork in the road. Whenever you reach a dead end or a loop, you can go back to the last intersection and try a different path. If your last left turn got you nowhere, you'd come back to that intersection and go right instead. You can think of this strategy as the one a headstrong mouse might use, running as deep into the maze as it can and turning back only when it can't go any further. This search strategy, known as depth-first search, will eventually get the mouse to the goal. The problem is, it might not be the shortest route, because the mouse only turns back when it needs to, so it may have missed a shortcut that it never tried. The sibling to this search algorithm, breadth-first search, would find the shortest path. With this strategy, the mouse runs down one branch of an intersection until it reaches the next one, and then it goes back to check the path it skipped before moving on to the next layer of intersections. So the mouse checks every option it reaches, but all that backtracking means that it's rerunning paths dozens of times. At this point, even searching the whole maze often takes less time. So why not just do that? A meticulous mouse could search all 256 cells of the maze, testing every turn and corner to ensure it has definitely found the shortest path. But searching so thoroughly isn't necessary either. Instead, the most popular Micromouse strategy is different from all of these techniques. It's a search algorithm known as flood fill. This mouse's plan is to make optimistic journeys through the maze. So optimistic, in fact, that on their first journey, their map of the maze doesn't have any walls at all. They simply draw the shortest path to the goal and go. When their optimistic plan inevitably hits a wall that wasn't on their map, they simply mark it down and update their new shortest path to the goal. Running, updating, always beelining for the goal. Under the hood of the algorithm, what the Micromouse is marking on their map is the distance from every square in the maze to the goal. To travel optimistically, the mouse follows the trail of decreasing numbers down to 0. Whenever they hit a wall, they update the numbers on their map to reflect the new shortest distance to the goal. This strategy of following the numerical path of least resistance gives the flood fill algorithm its name. The process resembles flooding the maze with water and updating values based on the flow. Once the mouse reaches the goal, it can smooth out the path it took and get a solution to the maze. However, it may look back and imagine an even shorter, uncharted path it could have taken. The mouse might not be satisfied that it's found the shortest path just yet. While this algorithm isn't guaranteed to find the best path on first pass, it takes advantage of the fact that micromice need to return to the start to begin their next run. So if the mouse treats its return as a new journey, it can use the return trip to search the maze as well. Between these two attempts, both optimized to find the shortest path from start to finish, it's extremely likely that the mouse will discover it, and the mouse will have done it efficiently, often leaving irrelevant areas of the maze entirely untouched. Floodfill offers both an intelligent and practical way for micromice to find the shortest path through the maze. Once there was a clear strategy to find the shortest path, and once the microcontrollers and sensors required to implement it became common, some people believed Micromouse had run its course. As a paper published in IEEE put it, at the end of the 1980s, the Micromouse contest had outlived itself. The problem was solved and did not provide any new challenges. In the 2017 All-Japan Micromouse Competition, both the bronze and silver placing mice found the shortest path to the goal, and once they did, they were able to zip along it as quick as 7.4 seconds. But Masakazu Utsunomiya's winning mouse, Red Comet, did something entirely different. This is the shortest path to the goal, the one that everyone took. This is the path that Red Comet took. It's a full 5.5 meters longer. That's because Micromice aren't actually searching for the shortest path, they're searching for the fastest path. And Red Comet's search algorithm figured out that this path had fewer turns to slow it down. So even though the path was longer, it could end up being faster. So it took that risk. It won by 131 milliseconds. Differing routes at competition are now more common than not, and even just getting to the goal remains difficult, whether due to a mysterious algorithm or a quirk of the physical maze.
The corner, it's a little bit like a whoa.
さあ小さなコーナーが待っているどうだこのスラロームでゴールインはどうでしょう
Micromice don't always behave as you'd expect.
なんですが実はこのマウスなぜか走行中に止まってフラッシュ書き込むときにフリーズするっていうバグを抱えていまして今4分ぐらい走ってたのでそれ起きたら僕はもう倒れてました
Micromouse is far from solved, because it's not just a software problem or a hardware problem, it's both. It's a robotics problem. Red Comet didn't win because it had a better search algorithm or because it had faster motors. Its cleverness came from how the brains and body of the mouse interacted together.
So it turns out solving the maze is not the problem, right? It never was the problem, right? But it's actually about navigation, and it's about going fast.
Every year, the robots get smaller, faster, lighter. There is still plenty of innovation left. And there's a small group of devotees in Japan busy building quarter-sized Micromouse, which would sit on a quarter.
Nearly 50 years on, Micromouse is bigger than ever. Competitions have appeared solved at first glance before. The high jump was an Olympic sport since 1896, with competitors refining their jumps using variations like the scissor, the western roll, and the straddle over the decades, with diminishing returns. But once foam padding became standard in competition, Dick Fosbury rewrote the sport in 1968 by becoming the first Olympian to jump over the pole backwards. Now, almost every high jumper does what's known as the Fosbury flop. If Micromouse had indeed stopped in the 1980s, the competition would have missed its own Fosbury flops, two innovations that completely changed how Micromice ran. After all, a lot can change in a sport where competitors can solder on any upgrade they can imagine. The first Fosbury flop was one of the earliest innovations in Micromouse, and had nothing to do with technology. It was simply a way of thinking outside the box, or rather, cutting through the box. Every mouse used to turn corners like this. But everything changed with the mouse Mighty 3.
So Mighty Mouse 3 implemented diagonals for the first time.
Oh, you sneaky devil, you!
And that turned out to be a much better idea than we really thought. And because it's cool, you know, maze designers often put diagonals into the maze now. So, you know, you could end up with a maze where it never comes up, but most of the time it's actually a benefit.
In order to pull off diagonals, the chassis of the mouse had to be reduced to less than 11 centimeters wide, or just 5 centimeters for half-size Micromouse. The sensors and software of the mouse had to change too. When you're running between parallel walls, all you have to do is maintain an equal distance between your left and right infrared readings. But a diagonal requires an entirely new algorithm, one that essentially guides the mouse as if it had blinders on.
Normally, if you're going along the side of a wall or something like that, you know, most of the time you can see the wall all the time. And so that helps you to guide yourself, and you know when you're getting off. But in the diagonal situation, you just see these walls coming at you.
And if you veer even a tiny bit off course, snagging a corner is a lot less forgiving than sliding against a wall. Diagonals are still one of the biggest sources of crashes in competition today. But in exchange, a jagged path of turns transforms into one narrow straightaway. These days, nearly every competitive Micromouse is designed to take this risk. Cutting diagonals opened up room for even more ideas. Around the same time, mice were applying similar strategies to turning. Instead of stopping and pivoting through 2 right turns, a mouse could sweep around in a single U-turn motion. And once the possibility of diagonals were added, the total number of possible turns opened up exponentially. The maze was no longer just a grid of square hallways. With so many more options to weigh, figuring out the best path became more complex than ever. But the payoff was dramatic. What was once a series of stops and starts could now be a single fluid snaking motion. How Micromice imagined and moved through the maze had changed completely. Available technology was getting upgrades over the years as well. Tall and unwieldy arms that were used to find walls were replaced by a smaller array of infrared sensors on board the mouse. Precise stepper motors were traded in for continuous DC motors and encoders.
The DC motors give you more power for less size and weight, and so we were interested in doing that. So then you have to have a servo, you have to actually have feedback on the motor to make it do the right thing.
Gyroscopes added an extra sense of orientation.
It's like a compass.
Yeah, absolutely.
You had this thing with you.
They came about because of mobile phones, really, so the technology provides people with things which weren't there before. All of the turning is done based off the gyro, rather than counting pulses off the wheels, because it's much more reliable.
But even with all the mechanical upgrades, the biggest physical issue for Micromice went unaddressed for decades. One thing you'll see almost every competitor holding is a roll of tape. Once you know to look for it, you'll see it everywhere. This tape isn't for repairs or reattaching fallen parts, it's to gather specks of dust off the wheels in between rounds. At the speed and precision these robots are operating, that tiny change in friction is enough to ruin a run. If you want to turn while driving fast, you need centripetal force to accelerate you into the turn. And the faster you're moving, the more force you need to keep you on the track. The only centripetal force for a car turning on flat ground is friction, which is determined by 2 things: the road pushing up the weight of the car, or the normal force, multiplied by the static coefficient of friction, which is the friction of the interface between the tire and road surface. This is why racetracks have banked turns. The steep angles help cars turn with less friction, because part of the normal force itself now points in to contribute to the centripetal force required. If the banked turn is steep enough, cars can actually make the turn without any friction at all. The inward component of the normal force alone is enough to provide the centripetal force required to stay on track. Micromice are no different, and they don't have banked turns to help. As they got faster and faster, by the early 2000s, their limiting factor was no longer speed, but control of that speed. They had to set their center of gravity low and slow down during turns to avoid slipping into a wall or flipping over. But unlike race cars, there wasn't anything in the rules to stop Micromouse competitors from solving this problem by engineering an entirely new mechanism. Micromouse's second Fosbury flop was almost considered a gimmick when the mouse Mokomo 08 first used it in competition. You might be staring at the video to try to see it, but you won't. Instead, it's something you'll hear. That isn't the mouse revving its engines, it's spinning up a propeller. And while flying over the walls is against the rules, there's nothing in the rules against a mouse vacuuming itself to the ground to prevent slipping.
Dave Otten was the first person I saw put a fan on a mouse, but he used a ducted fan, and I think he was really looking at kind of reaction force, blowing the thing down. He had a skirt around, but it was not terribly effective, forgive me for saying so. The idea is to let as little air in as possible, and like your vacuum cleaner, when you block your vacuum cleaner, right, the motor unloads and speeds up, and so the current drops. But if you let too much air in, the current's very high, and these are just quadcopter motors, and they draw a lot of current.
At the scale of Micromouse, a vacuum fan, often just built from handheld drone parts, is enough to generate a downward force 5 times the mouse's weight.
Wow, okay. That's impressive. So how much does the car actually weigh?
About 130 grams. And if you listen, I don't know if you'll get it on your microphone, but
oh yeah,
you'll hear the motors slow down, it loads up.
With that much friction, Micromice today can turn corners with a centripetal acceleration approaching 6 Gs. That's the same as F1 cars. Once nearly everyone equipped fans, the added control allowed builders to push the speed limit on Micromouse.
When it's allowed to, it will out-accelerate a Tesla Roadster, but not for very far.
And they can zip along at up to 7 meters per second, faster than most people can run. Every one of the features now standard on the modern Micromouse was once an experiment, and the next Fosbury flop might not be far off. The first four-wheeled Micromouse to win the All-Japan competition did so in 1988, but it would take another 22 years of the winning mouse growing and losing appendages before four-wheeled mice became the norm. With Micromice still experimenting in 6- and 8-wheeled designs, omnidirectional movement, and even computer vision, who knows what the next paradigm shift will be.
Your time on the maze actually begins only when you leave the start square. So he's not penalized for any of this time.
But if you want to get started with Micromouse, you don't need to worry about wheel count or vacuum fans or even diagonals.
It is, to my mind, the perfect combination of all the major disciplines that you need for robotics and engineering and programming, embedded systems, all wrapped up in one accessible bundle that you can do in your living room, and you don't need a laboratory to run it. You come along because you're curious, and then you think, I could do that. That doesn't look so hard. And then you're doomed, really. If it sucks you in, it turns into quite a journey.
10秒。いや、時間は問題じゃないんだ。スタートコンマ。頼む、行ってくれ。すごいです。
At its core, Micromouse is just about a mouse trying to solve a maze. Though nearly 50 years later, it's a simple problem that's a good reminder there is no such thing as a simple problem.
Micromouse is here and now. Take a chance and start creating. Micromouse will show you how.
A humanoid robot built for all the same tasks a human does sacrifices specialization in any one skill in order to be a generalist. But if it does all tasks semi-well, and these tasks are what humans are already doing, well then those robots are just overlapping with us, copying our capacities rather than expanding them. So robots are perhaps likely to enter our lives not as multi-purpose humanoids, but rather as precise tools we can pick and choose. Instead of one Swiss Army knife robot, you'd end up with something like a personalized toolbox of specialized robots. Big futuristic questions like how to bring robots into our daily lives requires all sorts of practical and creative skills. But perhaps the most important one is actually something that anyone can build: problem solving. If you want to hone your own ability to problem solve, you can get started on that right now for free with today's sponsor, Brilliant. Brilliant will make you a better critical thinker while helping you build real skills in everything from technology and programming to math, data science, and whatever you're curious about. On Brilliant, you'll learn through discovery, by trying things yourself. And you'll not only gain knowledge of key concepts, but learn to apply them to real-world situations, all while building your intuition. This gives you the tools to solve whatever problems come your way. You know, we've been partnering with Brilliant for years, and I still find new things to learn all the time. Like this course on how to maximize the value of an electric car. Brilliant has thousands of interactive lessons, and because each one is bite-sized, you can do it in just minutes. So no matter where you are, you can always be building a quicker, sharper mind right on your phone. To try everything Brilliant has to offer for free for 30 days, visit brilliant.org/Veritasium, or you can scan this QR code, or click that link down in the description. You'll also get 20% off an annual premium subscription. So I want to thank Brilliant for sponsoring this part of the video, and now dive into a surprising trait we're starting to build into robots. Elliot's Vine robot and jumping robot are just two cases where the robots that might save our lives or explore new planets don't look much like traditional robots at all. But soft robots in particular are an entire field of study. So why are so many researchers trying to build the robots of the future with soft materials? For one, trading out fragmented metal frames for single, flexible bodies might be how we make robots more reliable and precise. These bendy gearboards are so predictable that they were commissioned by the US government to secure nuclear weapons, ensuring that no random motions could accidentally set them off. But predictability is just one of 8 reasons that machines that bend are better.
What do this satellite thruster, plastic tool, and micromechanical switch have in common? Well, they all contain components that bend, so-called compliant mechanisms.
So it's always been considered to be bad to have flexibility in your machines. Well, we've tried to take that thing that everybody hates and is trying to avoid and say, how can we use flexibility to our advantage? How can we use that to do cool stuff?
Now, Professor Howell literally wrote the book on compliant mechanisms.
That's the most cited book.
But he's pretty nonchalant about his work. Just watch how he introduces this mechanism he developed to prevent nuclear weapons from going off accidentally.
Actually, it's safing and arming of nuclear weapons. And so
What?
if you want to
Hang on. What are nuclear weapons?
Safing and arming.
Safing and arming.
Yeah, so if there's anything in the world that you want to be safe that is not going to accidentally go off.
I feel like it doesn't even need saying, but yes, nuclear weapons, obviously you don't want them to go off. Well, I don't understand how this is going to keep nuclear weapons safe.
Now, I want to come back to this device and explain how it works, once we understand why compliant mechanisms are best suited to this task.
That's cool.
So let's start with something basic.
Probably the first compliant mechanism I ever designed was this thing. What it is a compliant mechanism that is a gripper. So you can put something in there and it'll get actually a really high force. I can put that in there and it breaks the chalk.
What if you put your finger in there and squeeze it?
You would scream in pain. Would you like to try?
I would.
Okay.
Like I would actually like to feel the force.
Okay. You need to squeeze it yourself though. Or
Really?
Well, all right. I'll squeeze till you scream in pain.
don't. Ah! That very quickly got incredibly painful. It felt like having my finger like in a vice.
That looks suspiciously like vice grips, but now with these flexible components where the hinges are.
What I learned in my visit with Professor Howell is that compliant mechanisms have a number of advantages over traditional mechanisms. But I thought he needed kind of a clever, pithy way to remember all of these advantages. So I came up with the 8 P's of compliant mechanisms. And the first of those is part count. Compliant mechanisms have reduced part count because they have these bendy parts instead of having things like hinges and bearings and separate springs. This gripper is just a single piece of plastic, but achieves a similar result to the much more complicated vice grips.
Like, how much does it amplify the force?
This will get about 30 to 1. So I can get, for 1 pound force in, get 30 pounds out. So
that's pretty good.
And
Seems like that would be super cheap.
And really inexpensive. So this we just made here in our shop, but you can imagine also injection molding that.
That would cost like cents.
Yep, this would cost cents. The other thing is, because of its shape, you could extrude it and then just chop them off. That would be cool.
So the simple design allows different production processes to be used, which lowers the price. These switches, for example, achieve in one piece of plastic what is normally done with springs, hinges, and many rigid plastic pieces.
Also a good fidget device.
How long can these last?
We've had these in our fatigue testing machine. We've been able to go over 1 million cycles without failure.
What do we got there?
All right, Derek, I've got a quiz.
Uh-oh.
A quiz for you. Okay?
Elephant.
Very good. Okay, I'm gonna push on the elephant's rump this direction. Okay, I'm gonna hold this, and that little dot right there is that dot. When I push on it, is it gonna go left, right, up, or down?
I just, you know what? I wanted to guess without even thinking about it.
Please do.
I'm gonna say like up and in.
Okay, up
and
and
in.
in.
And I kind of feel like that because like that would be a logical way for an elephant to hold its trunk more than. But also because like if this is all going over, I feel like this is gonna kind of extend there, and that's gonna get pushed up in there.
Good thinking.
Well, I don't know. Is that good thinking?
It's thinking at least. So this is designed so that when you push on that, it actually just rotates in space. It doesn't move at all.
I knew you were going to pull some sort of trick question.
It's a trick question.
Now, since I was fooled by it, I had to try it out on my friend, the physics girl.
That's so trippy. That is so cool. I don't understand. What?
It's modeled after the mechanisms you use in wind tunnels, where you want to have, say, a model that's attached here, but then you move it, and all you want to do is control its angle and not move it around in the wind tunnel.
Don't displace it, but be able to change the angle.
Devices like this demonstrate that compliant mechanisms are capable of producing very precise motion, which I personally found pretty counterintuitive because these objects are made up of flexible parts. But maybe that shouldn't be surprising, because compliant mechanisms don't suffer from backlash, for one thing. So backlash occurs when you have a hinge, which is basically just a pin in a hole, and it's moving in one direction. And now, if at some point the motion reverses, it doesn't happen instantaneously because there's some give in the hinge. This also causes wear and requires lubricant, and that is why compliant mechanisms have better performance than their traditional counterparts.
This one, though, is my favorite.
That is one of my favorites, too. It's just so pleasing. Right?
Oh, that sound is so satisfying.
This actually, believe it or not, was inspired when we were doing things at the microscopic level, where we're building compliant mechanisms on chips. We had to be able to make these compliant mechanisms out of silicon, which is as brittle as glass.
Mm-hmm.
And if you're trying to make something like this out of glass, right, it's crazy hard. But that also means once we figured out the design, we could make it in a material even like PLA, which is also, not the ideal compliant mechanism material. So you can get on our website and get the material and get the files to make this yourself.
I'll put a link in the description.
Yeah, that also has a nice feel and a nice snap to it.
It has a really nice snap. I like when it comes out, it's like gunk. Like there's something about that that's really, just very pleasing. So these things actually move?
Oh yeah.
I need to see this.
Okay, all right, we'll do it.
Were those etched on there?
Those are etched, and so just using the same processes used to make computer chips.
So another advantage of compliant mechanisms is that they can be made with significantly smaller proportions because they take advantage of production processes like photolithography.
And we have motion that we want at the microscopic level.
That's brilliant.
Plus, since they simplify design, compliant mechanisms are much more portable, meaning lightweight, which makes them perfect for space applications.
This here is something we did with NASA, making a hinge that could replace bearings for, say, deploying solar panels. This is titanium, 3D printed titanium. But what's freaky about it is you get that motion, which people expect, but there's a piece of titanium that can bend plus or minus 90 degrees, 180 degree deflection.
That is solid titanium.
That is one piece of titanium that is 3D printed.
There's no alloy, nothing to make it flexible.
Yep, this is, and even freakier than this is this guy right there. So that looks like a crazy beast, but every part in there has a purpose. All these flexible beams, here are the two inputs. And again, we did this with NASA for thruster application, where we can put a thruster right there. And now with our two motor inputs, we can direct that thruster in any direction. That titanium device moves out, and you notice that it's just all bending. And then there's no pinch points for the fuel lines or electrical lines coming in.
Here, this single piece of titanium allows you to use one thruster in place of two.
Okay, that is a clutch. Okay. So the idea is if you spin it up really fast, because it's flexible, this outer part will actually start coming outwards. And then if there's a drum around it, it'll contact with that drum and spin that thing.
Oh, so this like kind of, oh, that kind of comes out like so,
When
and
it
then
gets spinning really fast, and then you essentially engage this outer drum. So this is like the way that a chainsaw would work or something like that, because you get it spinning fast enough, and then it engages the chain, and then it turns it over, and then
force. Yeah. Wow, that's cool.
So here, this is made in plastic so that it, you can see it, but in reality, it's got to be a lot stiffer. So here it is made in steel.
What? So hang on, you're saying that thing, which is made of steel, you spin it up to a certain speed, and then it expands and engages a drum that's around it.
Yep. So it will idle with no motion, but then at a certain speed, that are what we designed it for, it'll speed up to that RPM.
You speed it up and it engages.
Yep.
I had no idea. Like, I have learned something today.
So let's come back to the safing and arming device for nuclear weapons. Its purpose is to ensure that no random vibrations, say from an earthquake, inadvertently disable safeties and arm the nuclear weapon. Now, one of the requirements was that this device be made as small as possible.
They had made those as small as they possibly could using traditional methods, even using things like what the Swiss watch manufacturers were using.
With compliant mechanisms, they produced a device out of hardened stainless steel, where some components were the size of a human hair. This is high-speed video. Here the device is operating at 72 Hertz, meaning this little hole makes 2 complete revolutions each second. The way it's meant to work is an arming laser shines on the rotor wheel, and when the proper input is given to the system, the wheel rotates a notch. If all the proper inputs are given, then the hole lines up with the laser beam, and crazy things happen from there. So it is essential that this device's performance is perfectly predictable, even if it sits unused in a silo for decades.
So, are these now being used on nuclear weapons?
It turns out they don't tell us what they do with their nuclear weapons. And so we designed them, we made prototypes, we tested them, and then it goes what they call behind the fence, and where it's all classified, and we don't know what happens. So.
But these soft components by themselves aren't truly robots. It's only once you combine them with computers that you get robots which can autonomously form crazy shapes or new styles of movement, all because they bend.
But how do they work? And why would you want a soft robot in the first place? So I came up to Stanford to meet Zach Hammond and his soft robot.
How's it going? All right, you want to tip it? So is the idea that the robot could walk this way?
Totally, yeah. So you can kind of chain these rolls together to kind of roll around in any environment. They call this punctuated rolling locomotion, wherein it's kind of stuck on a face until it tips over, and now it's on a new face, and it can then continue to move its center of gravity. Once that center of gravity exits the support polygon, or the base, then it tips over one of the edges of the face.
This is a different soft robot made out of flexible tubing. It was designed to mimic the way a turtle walks, where diagonally opposite legs move together. It's powered entirely by compressed air, and perhaps most impressive, it requires no electronics. All of the circuitry is pneumatic. And this means the robot can be used in places like mines, where electronics could spark explosions, or in the strong magnetic fields around MRI machines. But why would you want a soft robot in the first place?
One of the things that I like to do is just to take the robot and kind of like beat it up a little bit, show how it's compliant and compressive.
Well, because they're safer.
If you'd like to take a whack at it, feel free.
But I don't think this is your work. I don't want to break it, obviously.
No, feel free, go for it.
For operation around humans, there's not much damage a soft robot can do to you.
I can stand on these?
Yep.
This is a pretty crazy compliant robot.
Because the fundamental structure of this robot is compliant, there's only some maximum force that it could ever exert on me. So it's inherently safe to be operating around people.
Could we make it fall and have me be inside it?
Yeah, Yeah, we could do that for sure. Just watch your head.
Yep, if I go over here.
If you're there, yeah, we can do that.
All right, let's try it. Here it comes. Well, that's not bad at all, is it?
I can try another shape that's supposed to open up one of the faces so you can jump out of it quickly.
Okay.
I haven't tested it in a little while, so I don't know how it's gonna go, but let's try this. There you go, that's their face right there to your right, and you can exit the truss from that face.
Boom.
Perfect.
Just that easy. Did you build this by yourself?
Me and one other grad student built this entire thing ourselves, basically.
And how long did it take?
We did it in about a month, I want to say, like actually constructing everything.
And was it tricky? I mean, were you sewing that stuff?
Yep, we sewed this all ourselves.
The main structural members of this robot are fabric tubes inflated with air.
Yeah, so these red tubes are a nylon fabric, and then internally there is a polyethylene tube that provides the airtightness.
The tubes are inflated to about 6 psi above atmospheric, so it's almost 1.5 atmospheres. Each tube passes through pairs of rollers connected to a motor. The rollers pinch the tube so it bends kind of like a pinched straw.
The rods, and then we have this like high friction material wrapped around the rods. And then that coupled with the fact that we have this pressurized tube that's kind of pushing the membrane of the tube into the rollers prevents us from slipping.
By driving the motor, it changes the lengths of the tubes.
Kind of like when a clown creates a twist in a balloon and then folds that balloon into a balloon animal. The difference between what the clown does and what we do is that there's some passage of air between adjacent segments of the tube so that as the robot drives around, we're not pressurizing the segments of the tube.
This robot is made of 4 inflated tubes, each one connected to a pair of motors, forming triangular sides.
We also think that they kind of look like sausage links when put together, which is why we've named these robots after different sausages. So this one's called Polish, that one over there is chorizo, there's a linguiça and a kielbasa over there somewhere.
So what shape is the overall thing? It's an octahedron?
Yeah, we call it an octahedron because if you drew lines between these kind of kinematic joints here, it would create an octahedral shape.
Driving the motors together allows the robot to dramatically change shape. It can get very tall or short and squat. But since the tubes themselves don't change in length, the overall perimeter of the robot, the length of all the edges combined, doesn't change. So the robot is considered isoparametric.
How do you feel when you watch those Boston Dynamics videos?
Oh, I love those videos. They're so cool.
The Boston Dynamics robots are kind of terrifying.
Mm-hmm.
Like, isn't the idea with soft robots to like convince people that robots are good and soft and kind and friendly and safe?
That's definitely true. Yeah, there are some things that you can do to rigid systems to make them feel like compliant systems based on how you're controlling the motors. But yeah, they're definitely, you know, heavy, expensive, and can be dangerous if they're not used correctly.
The hard robots we're used to are strong and precise. Their actions are accurate and repeatable. But they are also heavy, and they can't really change their volume as dramatically. But this robot is still capable of carrying a heavy load.
So I have a GUI in MATLAB that
nice.
enables me to just put in the positions that I want the robots to move in inches and then send them out. There's some other functionality. I have some like stored configurations to send to the robots.
Soft robots also have the advantage of shape changing. They can become tall to go over obstacles or short to fit under obstructions.
So if there's some rock that it didn't see or that it wanted to roll over, it could simply do that, and the compliance of the tubes would simply just bend around that disturbance.
Do you imagine robots like this doing work in space?
Oh yeah, definitely. So one of the nice things about these types of structures is that they can shrink down their volume very drastically. And because volume on rockets is such an expensive premium, being able to have a robot that can pack down small for transport is very valuable. So NASA was at one point looking into truss robots for exactly that reason. And they've contacted us since we've made this robot to explore different ideas for space exploration projects. So one of the things that they're thinking about doing is deploying robots underneath a sheet of ice. So they're going to drill through this sheet of ice and then deposit a robot through what is kind of a small diameter hole. And so if you can have a robot that can change its volume very drastically or be disassembled and then reassembled to form like a much larger structure, then you can have large robots that are able to fit through these tight spaces and be deployed in kind of difficult to access areas.
Is this a little bit like an octopus? Is that how you could think of it?
There is some connection there because they use their shape-changing ability and their compliance to squeeze through tight passageways and then also to wrap their body around objects. So for example, they can open jars with their tentacles. And one of the things that we want to use this robot for is grasping and manipulating objects.
This robot is even capable of picking objects up off the ground.
We'll try that and see if it can grab it. Because of the compliance of the tubes, it has a natural ability to grasp and manipulate objects because as it does so, the tubes bend ever so slightly, which increases the contact area and distributes evenly the forces that are exerted on that object.
So, I mean, is the biggest risk if it pops?
Yeah, that's a big risk. I mean, you obviously need the compressed air for your structure, and so if you have a leak, then you don't have a robot, right?
It's a pretty big drawback of soft robots.
You know, some things that you could do to mitigate that would be to have on board a small compressor, which isn't there to provide power to the robot, but would help you maintain pressure if there were any small leaks.
When you tell someone you're working on a robot and they see this, does it defy expectations?
Totally. They have no idea what it is I'm talking about until I show them like a video or a picture. I think most people's conception of soft robots was really expanded by the movie Big Hero 6. And I think they did a great job in kind of showcasing what a soft robot can do and why they're useful, and kind of just popularizing the notion. It's really great to have compliance built into any mechanical system, especially as we want robots to work closer and closer with humans. So I think we'll definitely see more soft robots in the future.
So maybe robots will enter our daily lives sooner than we think, just not in multi-purpose humanoid form. In fact, one specialty robot is already becoming widespread, the glorious Roomba, built for maximum vacuuming.
Do you think the way that robots integrate themselves into our lives will be like, you know, a humanoid robot in your house? Or will it be, you know, specialized kind of little things that we don't even think of as robots, but they sort of
slowly infiltrate? Yeah, I think probably the latter is going to happen first, would be my guess, right? I mean, you know, little things like, yeah, like things just start getting smarter, you know, whatever it's your shoes or your watch or your car, right? And your thermostat and all those things. And then before like your maid, you know, shows up as a robot.
By dropping the human model of a robot, instead we can choose the best possible shapes and materials that maximize specific abilities. And with this method, we've already built robots that can save your life, leap tall buildings in a single bound, move with super speed, protect your valuables, and shapeshift. You know, come to think of it, they'd make a pretty good superhero team.